Okay, so welcome to the first review session for Engineering 210 circuits. In these review sessions, it'll basically be me going over kind of what you've learned in the past week, and mainly the bulk of the time is going to be spent doing practice problems, and I'll talk through them as thoroughly as I can. If you have any questions anywhere along the way, feel free to either say something in chat, and I will do my best to read that consistently. Or just speak up and ask a question. If you have any questions, like I'm here to help you out. So yeah, without further ado, I will just kind of go over what we all have been learning and what you should know at the moment. Just one more second. Um, Here. Okay, so Engineering 210 review session one. Yep. So, most basic thing that you should know in this class is Ohm's law. Hopefully, a lot of you learned this in physics or other classes. And at the base, it's V equals IR. You use this to basically solve every problem in some way or another. So, at the most basic level, that means if I have some resistor and it has some current going through it, that has some resistance in ohms, it has a current I, then the voltage that will be dropped across that resistor is equal to the product of the resistance and the current. So for example, if I had a 50 ohm resistor and there were 2 amps going through it, then it would drop 100 volts. Those are kind of big numbers. I just thought of those on the spot. So you probably won't have something like that in one of your questions, but yeah. Okay, next up, power. So I'm just kind of gonna breeze through the things that will be directly relevant to the quiz. If you have more like fundamental questions on the class, I would recommend going to office hours. So this is more of a place to really just mainly do practice problems. Yeah. So power equals the current times the voltage. So here, let's say we have some unknown device, but we know that there are 3 amps going into it, and over it there is a voltage drop of 6 volts. Then the power dissipated by this device would be 6 volts times 3 amps, which is, 18 watts. And this brings us to the passive sign convention. So the passive sign convention basically tells you whether or not power or voltages are positive or negative in some scenario. So the way that I remember it is that things are all positive when the voltage drop is in the same direction as current flow. This will become relevant soon in the class. I think you guys have kind of. Oh, yes, the recording of this will be sent afterwards. I'm going to post them all on like a Google Drive. So keep that in mind if that's useful for you. Oh wow, I have a lot of people in here. Holy shit. Okay. Um, but okay, moving on. Again, voltage drop is in the same direction as current flow. Most people got this, but grading homeworks, I saw that there were a couple people who just got it completely backwards. So if that's you, make sure you understand this. So for example, this example from before, it's positive when I'll just use a resistor here as the example. It's positive when the voltage drop, basically for a resistor, it's always going to be positive because a resistor always dissipates power. The key thing here is power, positive power is dissipating power. And negative power is supplied. So the way you interpret this part is for things like a battery. So if I have a voltage source, right, what we see here is, let's say this is a 6-volt voltage source. The voltage drop for this component is from right to left. So that's the direction of the voltage drop. But the current that this produces will end up being to the right. So as we said in this part above, of course, here, if the voltage drop is in the same direction as current flow, then it's positive. So here, this would be thought of as negative. So if this was like 3 amps, then this would be the power equals 3 amps times negative 6 volts, which would be negative 18 watts. Forgive my handwriting. I'll go over like resistor stuff as well, but I think it'll really just be the most useful if I get into practice problems, and um if you guys have specific questions, just ask them and I can answer them because we can talk to each other. So then resistors. Oh, I'll do resistors and then like source transformations. And I think that's kind of everything that was on your homework. So I think generally the stuff on your homework is what's going to be on the quizzes. It kind of changes year by year exactly what's on there, but you'll see. So resistors. Two resistors in series are the same as one bigger resistor. So this is R1 and this is R2. These, you can kind of combine them into a resistor with the value R1 plus R2. This kind of makes sense if you think of a resistor as like some piece of material that resists electricity. If I take a little piece of resistive stuff and smack it onto another piece of resistive stuff, it's just a longer piece of resistive stuff. Conversely, if I have two resistors in parallel, then these less intuitively become one resistor with a value of R1, R2 over R1 plus R2. This kind of seems like it comes out of nowhere, but what it really is it's 1 over R1 plus 1 over R2. This whole thing, so like this can be extended to as many resistors as you want. Same with this thing. This equation here, I don't exactly remember the reason why, but the total resistance, the inverse of the total resistance the inverse of the resistance is sum to some total resistance. So this is where you get that. And so you can see if you were to flip this over, then you get something like that. But that's how resistors in parallel work. There's some kind of funky stuff with resistors in parallel, or with things in parallel in general. So you might get something like this and be like, oh, I don't know what to do with this. Give me a sec. You'd be like, oh, I don't know what to do with this. But what you see here is that these resistors are actually still in parallel. For two things to be in parallel, they just have to be connected by wires at both ends. Even though these like have something in the middle, they're still connected at both ends. If you think of like the wire as like a big metal plate, even if you have something in the middle here, if I have a resistor here and a resistor here, they're still connected at both ends, and you can think of them as in parallel. So that would still work. One other thing, the same idea goes for things in series. So if I have like a resistor here, a voltage source here, and a resistor here, and some other crap over there, even though this voltage source is in the way, this can still be simplified to something like this. Because as long as the resistors are on the same path in series with each other, then it still all works out. As a reminder, series is when things are like in a row, and parallel is when things are connected on both ends. Hopefully you all know that. If you don't, probably go to office hours. Okay, then two more things, and then I will get to practice problems for real this time. So Kirchhoff's laws. This is like one step up from V equals IR as being the basis of everything you'll do in this class. So what we have here is that Kirchhoff's voltage law states that formally it's like the sum of all voltages around a loop is equal to zero. So what that means is if you remember when we talked about if you remember when we talked about the passive sign convention, we mentioned how we think of voltage sources as negative. So if this is like 6 volts and and these all have some kind of resistance, what we're going to see is that this 6 volt source, we think of this as negative. So this would be minus 6 volts. And then let's say each of these is like a 2 ohm, 2 ohm, and 2 ohm. By something that you'll learn about either already or a bit later in the class, you can really quickly figure out what the voltage drop over these is by something called voltage division, where basically if you have a bunch of resistors and they have one voltage source, each resistor gets like the proportion of the voltage equal to like its proportion of the total resistance. So here it would just be, I guess a better example of this to make the numbers a bit more clear would be like this is 9 volts. So then since all three of these have the same resistance, all of them would have a voltage drop of 3 volts. So here, for this example here, we're saying around this loop and around any loop in any circuit, this will apply. The voltage, the total sum of all the voltages, assuming you follow passive sign convention correctly, will be 0. So here it would be -9 plus 3 plus 3 plus 3 equals 0. Wow, that makes sense. Cool. So now for KCL, we have that the sum of all the currents going into and out of a node are equal to 0. This one is kind of a lot more straightforward in my mind. So if we have some intersection of a bunch of wires and there's some currents going in and out, uh, then what this is saying is that the total current going in is equal to the total current going out. So there can't be like current going somewhere and not leaving. It's always going somewhere. So if I have like 2 amps here and 3 amps here, that's 5 amps going in. There has to be some combination of 4 amps going out as well. Um, in terms of signs, we say that currents going out. So I'll write this down. Currents going out of a node are positive. So keep that in mind. Is very useful. Or it's not really useful, but if you do that wrong on your homework, or on your quizzes, it'll really annoy your TAs and we'll laugh at you when we're grading your stuff if you get that backwards. Because there were like 3 people last semester that just flipped it for no reason and then like wrote, please, I flipped this because it makes more sense for me. So even if it makes more sense for you, just think of it this way because this is the convention and this is how, if you take any other circuits class, they'll expect you to do it. Okay. And now I will get to actual practice problems. So let's see. I think it's quite likely for this first quiz, judging from last semester, you'll probably be mainly talking about like mainly be talking about power. So I'll just show you one example question here. Give me a second to draw out this circuit. And again, if you have any questions while I'm going here, because I'm going to go through the circuit pretty fast, because I have a lot of experience with this kind of thing. If you have any questions, say them in the chat. Hopefully I will look over in not too long of a time and it'll be fine. So here, the question is saying, and here is labeled as Vx. So find Vx and power of 10 amp source. So oh wait, I should talk about one more small thing before I get into this. Source transformations. I don't really think you've learned this yet, but wait, no, it was on your homework. So you have. Source transformations. If I have a voltage source and a resistor in some kind of fashion like that, and this has V and R. This is exactly equivalent. Like there's no difference. You can replace them. Assuming these are the only connections, you can replace these. This is the exact same as a current source in parallel with the resistor. Again, make sure you're really looking at the connections here, where it's the same resistance and the current here would be equal to V over R. Similarly, you could go back the other way and the voltage would be the, again, it's just like V equals IR. It works out. Okay.
I have a quick question.
Yeah.
Just in the textbook for KCL, they say that it's positive if if it's entering. So are we just supposed to go against the textbook?
I think are you sure?
The very first bullet point says sum of all currents entering a node equals 0.
Okay. Well, yeah, sum of all current, if it's basically just saying if you think of all currents as entering, then it's the point of it is that there's no like current stored in the node. I think that wording's a bit weird, but what you'll see in this class is that currents going out of a node are positive.
Okay, thank you.
Yeah. Okay. Okay. So here, back to this question, it says find the power of the 10 amp source and find Vx. So when I see a question like this, the first two things you should always look at are Kirchhoff's laws and which one of them is going to be the most useful. That's probably what you're going to be doing here because you can't find anything here directly. So some like mistakes that you might make, you can't just directly say, okay, there's 10 amps here and there's 3 ohms here, so this is going to be 30 volts. You can't do that because there's also this going here, which would add other current into this 3 ohm resistor. So these two things both exist at the same time. So it's not as simple as you'd hope it would be. So what you have to do instead is kind of just decide to do KVL because you want to find a voltage, and Kirchhoff's voltage law would probably be a pretty good way to do that, right? So there's a couple ways you could go about this. Actually, I know I just said this out loud, but converse, it's different from what you would think and what I was just thinking in my head. Because of the like node nature of this, that's not real words I just said. But what do they recommend doing here again? Uh, actually, yeah, you're going to use KVL. So here, we're going to look at the voltage in this loop on the right. So remember, it's that the sum of all voltages in a loop is 0. So here, what we have is that, wait, KCL and KVL, what are they doing here? Oh, you actually have to use, sorry, I'm looking at a question with an answer key from previous years, and I'm not sure I fully agree with what they did or their method of doing it. And okay, so actually we're going to start by doing KCL at what we're going to call here is V1, or it's equivalent to Vx. Or I'll call it V1. So at V1, for doing KCL, we're looking at the currents going into and out of this node. So again, currents going in, we have this 10 amp here because if there's 10 amps created by this current source, that's going to go around this corner here. So here we're going to have negative 10 amps because it's going in, it's negative. And then we kind of just have to guess directions for the other currents. So let's just assume that this current's going in here and this one's here. We're going to call kind of arbitrarily, we're going to call this one I1, this one can be called I2. And since we said I1 goes in, we can say minus I1 and plus I2, and that's going to equal 0. So then we have one equation and two unknowns. So we need one more equation to get two equations and two unknowns. So what we can do there is go to KVL. Kirchhoff's voltage law. So what we have now is that is going to be, if we look around this loop, then we have a bunch of resistors and one voltage source. So Kirchhoff's voltage law, again, is saying that the voltage is this thing. So we look at the voltages around the loop. So here, it'd actually be a bit better if we think of this as going the other way, because that's the direction we guessed I1 is going, so that would line up better. So here, we're going to have that negative 10 volts, and then plus, because resistors are always going to be positive, basically. And if so, remember, if we said I1 is there, then it's going to be the same I1 like all the way around the loop, because you can only have one current through any given path. Current doesn't change. Someone asked if you put current as going the other direction, would your answer be wrong? You won't get a different answer. The math should end up working itself out. It should be fine. You'll just like get a negative answer at the end, but you'll get like, so like if I said I1 points this way, then my final answer for I1 would be a negative number. And so if I have a negative number pointing in that direction, then that just means it's actually pointing in that direction. It means you guessed wrong, but you'll just get a negative number and that's fine. So as long as you do the math correctly, everything should work out regardless of what directions you guess. So here it would be 10 volts plus, and then remember V equals IR. If we want to find the voltage drop across this, it's going to be 3 ohms times I1, because I times R. And then for this 3 ohm resistor, for the other 3 ohm resistor that is, it would be 3 ohms times I2. And then for the final one, remember, if the I1 is here, then I1 is also here. So it would be plus 4 ohms times I2 equals 0. And so if we combine terms, we get 7I1 plus 3I2 equals 10. And then we can solve this however you want. I'll show real quick. If you're doing this on a homework, you can just like use an equation solver. You probably should just use an equation solver because it'll take way too long. On the homework, sometimes you have like 3 equations, 3 unknowns, and that's like, it's just a pain. But on a quiz, you don't have access to that. So here, let's say if you shuffle things around, you get I2 minus 10 equals I1. Plug that in, we get 7 times I2 minus 10 plus 3I2 equals 10. 7I2 minus 70 plus 30I2 equals 10. I think I'm doing this right. And then 10I2 equals 80. So then I2 equals 8. Yep.
I had a
And
question.
yeah,
Wouldn't the resistor, the 3 ohm resistor in the middle, have both currents I1 and I2 going through it?
so good point. The thing is, it has I1 and 10 amps going through it. So remember, Kirchhoff's current law says that if we have some nodes like this, and we have a current going in here and a current going in here and a current going out there, then they all sum up to 0. So if let's say this is I1, I2, and I3, we'd say that, remember how we talked about the signs? So it would be positive I3 minus I1 minus I2 equals 0, which again, or which simplifies much very sensibly to this equation, which honestly makes more sense, right? It's saying that the down current is the sum of the two going in. Here, that's basically what we were saying with this equation. I just didn't really emphasize that at the time. So here, what we're actually saying is that I2 equals I1 plus 10. I probably should have written that here instead, because then I could have made that point. But as you can see here, like there's basically in this path, because of the current source, in this path, there's 10 amps, and in this path, there's I1. And then they combine to make I2 here. And we're trying to figure out what I2 is. That our goal is to figure out what I2 is, because if we find out I2, then we can find the voltage here, because V equals IR. Yeah. So, and now we found I2. So we could find I1, but it's actually not really necessary for this question. I'll do it anyway. So just I2 minus 10 equals I1. So then I1 equals, oh, is this the case? I1 equals, funnily enough, I1 is negative 2 amps. So what that means is that I1 is actually going in that direction. So that goes back to that question that someone asked earlier. How do you know that the 4 ohm resistor will have a current of I2 rather than some combination? Okay, so with that, I'll finish the question, then I'll get to that. So I2 is 8 amps. So then remember, our original question was to find Vx. So Vx is the voltage of that 3 ohm resistor. V equals IR, so it's going to be I2 times 3 ohms, which is 8 times 3, which is 24 volts. Hopefully that makes sense. Okay, then the second half of the question was the power of the 10 amp source. So here, remember, power equals current times voltage. So we want to find so we have the current through the current source because it's like given right here, but we want to find this voltage. However, we've already actually found that voltage. So remember, things are in parallel if they have the same connections. So that means that this resistor and this current source are in parallel. And things that are in parallel have the same voltage. I don't think I said that earlier, but that is the case. So these are in parallel, and we just found Vx. So what you'll find is that this current source actually has the exact same Vx. So what that means is that there's also 24 volts across the current source.
不大呀，
You have a question?
啊，人不大，
Okay. Um, and then
不在这儿
I think
上课吧？应该他说5点钟还
Chong
有课。
Chong, could you mute yourself? Sorry. Okay. Um, so going back to passive sign convention, if we want to figure out the power of this 10 amp source, it's going to be the current times the voltage. And here, what sign are we going to give this voltage? So if we go back to what I said earlier, it's positive if the voltage drop is in the same direction as current flow. Here, the voltage drop is from top to bottom, but the current's going from bottom to top. So that means this is a negative 24 volts. And that would give us a power of negative 240 volt or negative 240 watts. Make sure you include units. You'll get like a little bit of points off if you don't. So, and if it's negative 240 watts, that means it's supplying power. You don't have to say that unless it says you have to, but yeah. Okay. Let me look at the questions that I've missed here a bit. Wouldn't the 4 ohm resistor? Okay, so for this 4 ohm resistor, someone asked about did I mess something up? Hmm. Yeah, I did make a mistake here. Kind of. Did I? I got the answer that they got in the key that I can.
The math is fine. It's just that for the 4 ohms, it should say I1, not I2.
Ah, yeah, that would do it. Okay. Yeah. So thank you for calling that out. Since I1 is here, I think I said this. Yeah, I said this as I was doing it and then wrote the wrong thing. Since it's I1 here, there's only one path for the current to flow, so you also have I1 flowing through the 4 ohm. Yeah, I wrote that wrong, but luckily I did the math right. Okay, so generally, if you have a question in this class so far, it's just going to be like use Kirchhoff's voltage law and use Kirchhoff's current law. And the goal is always to just get a bunch of equations and a bunch of unknowns. And until you have like 2 equations, 2 unknowns, 3 equations, 3 unknowns. And then once you have that, it is solvable. In upcoming weeks, when you learn some other things, there will be quiz questions that are just like, write out all the equations you would need to be able to solve this problem. You don't actually have to solve it because it would be like 5 equations, 5 unknowns, but write out all the equations that you like would need. Okay. Um, Someone asked, why is the power negative? So let me go over this again. This is kind of busy now, but let me switch colors. So remember, from the first part of the question, we found that Vx is 24 volts. Vx is the voltage across this resistor. So what that's telling us is that between this end of the resistor and this end of the resistor, there is a voltage drop of 24 volts. What we look at now is that, okay, this point is connected to this point by a wire, and this point is connected to this point by a wire. Wires have 0 voltage drop. So the voltage at this point is the exact same as the voltage at this point, and the voltage at this point is the exact same as the voltage at this point. So if we have a voltage drop of 24 volts here, then that means we also have the same voltage drop of 24 volts here. So now we have this 24 volts voltage drop across the current source, and it's given that the current source is giving 10 amps in that direction. So then we have 10 amps and 24 volts, and we find the sign because, again, it's positive when the voltage drop is in the same direction as current flow. Here, the voltage drop is in the opposite direction as current flow. The voltage is dropping in this direction, but the current is going in that direction. So we call it negative. Yeah, hopefully that clears it right.
Sorry, with that question, like, was it given that there was the positive and the negative in those areas as
Um, it,
problem?
I mean, when the beginning of the question states that Vx, I'll go to blue now. The beginning of the question, like when you're given the question, it's like Vx is like that. That's what you're solving for initially. And then when we find I2, when we made up I2, basically, when we called this current I2, we guessed that it was going down, right? And then when we found a positive number for I2, that basically means our guess was correct, right?
Yeah.
So then I guess going back to basic resistor stuff, if I have a resistor and I have current flowing that way, then the voltage drop is that direction.
Sorry, I'm talking about the 10 amp.
Yeah. So then once we found this 24 volts for the resistor, we're saying that the voltage here is the same as the voltage here, and the voltage here is the same as the voltage here. So if we have plus minus and it's 24 here, then we also have plus minus 24 volts here. Does that make sense?
Okay, thank you.
Okay.
Could your current, like, if we had the arrow going the other way, could the current, like, could you enter in the positive side of the voltage source?
Yeah, so yeah, actually you do here. So as I said here, if this is 8 amps and we have this equation from earlier, then yeah, I1 is going to be negative 2 amps. Uh, so yeah, you actually would have 2 amps going this way. That's kind of weird to think about, but if you think about, this is just an example, if I had like a battery that was 10 volts here and it's connected through some resistor to a battery that's like 2 volts here, then you can kind of imagine this one would overpower that one and the current would end up flowing this way in a loop. So you would have current going in that way. So it can happen. It's just like not really useful for a battery. However, you will be seeing that a fair amount in this class, just because this class is basically theoretical entirely, except for the lab component. But you'll see this in like questions and homework and quizzes and stuff. It's
So
not
does the arrow define the, like, the head of the arrow, will that always be positive and the tail be negative?
um the arrow I drew here is just like is just a drawing. The For a voltage source, like this is just saying on this side, if I have 0 volts, then on this side, I will always have 2 volts higher than that. If this side I have 8 volts, this side is 10 volts. It's basically a separation between two voltages. The voltage source says nothing about the current. The current only shows up if I then have a resistor, because the resistor, so like if I have this, then there's no current because there's no way for current to flow. But if I have this, then now I have a path for current to flow. I have some voltage here. Then current can flow, right? But all this voltage source does is it says the difference between this point and the difference between this point is 10 volts. However, then that makes the current flow, because if I have 10 volts on this side of the resistor and like 0 volts here, then I have a voltage across the resistor of 10 volts, and V equals IR for resistors. But yeah, don't get too hung up on that, I think. Okay, you do it with the right one. With the question in chat about if you do it with, you said if you do it with the loop, you get negative 10 amps equals I1 plus I2. So yeah, if you make the loop, if you guess that I2 is going that way, then yeah, you would get that 10 amps equals I1 plus I2. And then you'd do all the same math and it would work out fine. It's just at the end, you would then get a positive 2 amps for I1. And it would be fine. I'm saying the math works out. It's just if you get a negative number, you guessed the wrong direction. If you get a positive number, you didn't. I have a few more practice problems. I'm gonna keep doing those because I think that'll be the most useful thing. I'm gonna do one about source transformations here. Okay, so source transformations. The question says like use source transformations to find power of 12-volt source. So source transformations, if you remember, you can take, we'll copy this over. So you can turn a voltage source in series with a resistor into a current source in parallel with a resistor, or vice versa. So here, we have to see what kind of structures of like those already exist. So I'll point out one here. That one's pretty nice, right? And that's actually it. So don't get tricked and think that this is equivalent to this. Because remember, you have to look very closely at these connections. What you have here instead is, if I were to redraw it like in a different way, there's like too many connections here. So this would be equivalent to if I had the resistor here, but then this is connected between them. So this would be like if I had another thing here, and then that messes everything up. So you really have to make sure you only have these two in parallel, or you only have something in series. So I'll do the first source transformation. So I turn this into this. So that current source will become a voltage source. So the way that works, V equals IR. So voltage is going to be the current times the resistance. So this is now 8 volts. The resistor stays the same, and the rest of the circuit also stays the same. The resulting current source is going to be in the same direction as like the minus to plus. That kind of makes sense, hopefully. It's like if the voltage source is raising the voltage that way, then the current's going to be going that way as well. Okay. So that would be like your step 1. And now we can do another source transformation. Or we can do a simplification, actually. And I also missed a wire. That would, did I? Oh, no. Okay, yeah, we're good. So we have 8 volts and we have 8 volts. And now, just like I said earlier with resistors, where was this? Here, I kind of left something out, but you can do the same thing with like voltage sources. So if I had, let me, so if I had like if this was V1 and this was V2, then you could combine these to V1 plus V2. This isn't like quite accurate actually, but actually no, that's accurate. Ignore me. Okay, so then, as I said though, so you can combine these two to something like this. Okay. And now that we're here, what do we do next? We want to keep simplifying things. And the goal, again, is to find the power of this 12-volt source. What that means is that we actually cannot do anything to this 12-volt source. If you do a source transformation to that 12-volt source, then you no longer have the source that we want to find the power of. So you basically have to do everything except change this. So now that we're here, we have this. We can actually source transform it back into a current source, and you'll see why that's useful in a second. So this is going to be now and this would be 16 over 2, because if V equals IR, then I equals V over R. So this would become 8 amps, 2 ohms, 4 ohms. And now we have these lovely two resistors in parallel. So the new resistance will be that 2 times 4 over 2 plus 4, which is 8 over 6, which is like 8 over 6, which is 4 over 3 ohms. So this then becomes this. I drew those first couple way too big, it seems. And we're almost done. We need to do one more source transformation of this back into a normal, not normal, back into a voltage source. So the same way we did earlier, we're going to have, oh, these numbers kind of get nasty, but it's going to be 4 times 8, so 32 thirds voltage source. Kind of disgusting, but that's how it goes. We're here. So now, remember, the whole reason we did this is because we need to find, I guess I should have said this at the beginning, we have the voltage here, right? It's 12 volts. We need to find whatever this current is. So we did all the simplification so that we could get this to one circuit that is very easy to look at the current of. So 32 over 3 real quick, just to like get a ballpark, is like 10.67, 10 and 2/3, if I did that right. So what we can look at here is that this resistor has some voltage drop. If we think, okay, if we have the same voltage here and here, then let's say we call this 0 volts. That's the symbol for ground, which which you'll see in class a lot as 0 volts. It's also sometimes drawn as a little arrow. I personally like this one more. I think they probably have different meanings in schematics, but like one of them is like physical ground and one of them is like ground of your circuit. But they both mean 0 volts. So if we just kind of arbitrarily call this 0 volts, then up here we're going to have 12 volts, and up here we're going to have 10.67 volts. We now have, so that will actually make a current flow through that resistor. I'm running out of space here. I did not manage my space very well at all. So we're going to have, well, what will be the current? So V equals IR. So that means I equals V over R. The voltage across this resistor is then 12 minus 10.67, and the resistance is 4/3. 12.67, this is like 4/3 over 4/3. Wow. Crazy how the numbers work out sometimes. And this would be 1 amp. And it's 1 amp going this way, because that's the direction of the voltage drop. And then last but not least, now we need the power. So if we have, let's go back up here, zoom in on this 12 volt source. We have 12 volts, positive minus, and we have going up, we have 1 amp. Then our power is equal to 1 amp times, and then is this going to be positive or negative? Again, we say, what direction is the voltage drop? Here, the voltage drop is going down. It's positive if the voltage drop is in the same direction as the current. Here, it's in the opposite direction as the current. So here, this is negative 12 volts. And here, then finally, we get the power associated with this source as negative 12 watts. Yeah. Gonna take a sip of water. If you guys have questions, speak up or say them in the chat. And I think I have time for like one more problem. Can you explain how I got negative again? Yeah, so you understand at the end we found we found a current going this way through the resistor because it's 12 volts here and it's a lower voltage here, and current will flow from high to low voltage. Since it's flowing this direction here, it's flowing in the whole loop like that. And if it's flowing like this, then that means through this source, it's going up. So then up here, I just kind of zoomed in on that source. We have 1 amp going up, we have 12 volts, and the voltage drop is in this direction. This arrow here is just me drawing. This is not like a real thing. But the voltage drop is going down while the current is going up. Again, if we look to that golden rule I said, if the voltage drop is in the same direction as current flow, then it's positive. Here, the voltage drop is in the opposite direction as current flow. The voltage drop is from top to bottom, but the current flow is from bottom to top, so we say it's negative. And so we say 1 amp, negative 12 volts, and then 1 times negative 12 is just negative 12 watts. Okay, and then let's see, what do I want to do here? Okay, I'll do this question. This question also brings in dependent sources, which I didn't touch on, but hopefully you've learned them in class. They're pretty straightforward. This says use Kirchhoff's laws to find power of 0.2 amp source. So here we have 0.2 amps. We have V1 over 4. We have 4 ohms, we have 2 ohms, and we're labeling the voltage across this resistor as V1. So if we want to use Kirchhoff's laws here, then I look at this and I say, okay, there's like a pretty straightforward junction here and here. I'm going to pick one of them and do a Kirchhoff's current law. Will there be anything from Wednesday? There shouldn't be anything from Wednesday on the quiz. Generally, again, the quizzes will be what is on the homework, but maybe like a bit different. Okay. And how do we know when we add voltage sources and how do we subtract them? Again, it all comes back to passive sign convention. If you're asking about them in series, if I have a voltage source like this and a voltage source like this, and this is like 2 and this is 6, here you see they're in opposite directions. So here you'd like subtract them. But if this was -6 or like, because if this is 6 and it's in that direction, I'm going off on a tangent about something that was asked as a comment. This is equivalent to like that. And then you here, since they're in the same direction, this is equal to, I'm not explaining this well, but it all comes back to like assuming they're in the same direction, this is V1, this is V2, then this is V1 plus V2. And if they're in series, you can always do that. If they're in parallel, you're never going to have voltage sources in parallel. That's like not a thing that can happen. It wouldn't make sense. Okay, back to this question. I'm going to call this V1. We have one current going in here, one current going in here, and one current going down there. So I'll call this I1. So we have minus 0.2 minus V1 over 4 plus I1 equals 0. And then we can do a Kirchhoff's current law. I'll do it around the left side because we know what that current is. And we're going to say, actually, wait. Yeah. Hold up. V1 equals, oh, yeah. So we have, we know that I1, wait, I'm floundering. Hold up a sec. Give me a second to actually look at what I'm doing. Yeah. Oh, okay. Yeah. Currently, we have two unknowns. We have I1 and V1. We can relate those two very straightforward because V1 here is equal to 2 ohms times I1. Hopefully that makes sense because we have I1 and I1 is here and I1 goes through 2. And if V equals IR and we have V1 equals I1 times 2 ohms. And that's how we get that. So, but the point of this again is you just write equations that work for the circuit. And here we get 2 equations, 2 unknowns, and we can plug things in very directly. So now, if I plug in that second equation to the first equation, we have 2I1 over 2 plus I1 equals 0. And did I mess something up? Because this looks like it will get me, because this is a 4, not a 2. That would do it. Okay, so then we have minus 0.2 plus 1/2 I1 equals 0. If we do Wheeler algebra, you'll get I1 equals 0.4. So if we have I1 equals 0.4, then again, remember, we want to find, the goal of this is to find the power of the 2 amp source. So that means we need to find this voltage difference. I should have said that at the beginning, but always look at what you're trying to get in the end. So we're trying to get this voltage difference here. Since these are connected, that means we're also, the easier way to do it is to, or the only way to do it is to find the voltage difference here, right? So now that we found I1, we can directly find this voltage difference. Remember, 2 resistors in series, oh, I'm pressing the undo button, not the pencil button. 2 resistors in series is the same as 1 resistor of a bigger value. So this 4 and this 2, we can think of as a 6. And then the voltage difference, I'll do like a funny drawing here. So now we have like a big 6 ohm resistor. And then the voltage difference between here and here, which is the same as here and here, is then going to be V. So if I wanted to write this fancily, it would be V of the 0.2 amp source is equal to the voltage of the 6 ohm that I just made up plus, which is equal to 6 ohms times I1, which is 6 times 0.4, which is 2.4 volts. Yeah. And then, so what that tells us though, is since I1 is going down, again, I1 is going down, when you have a resistor, the voltage drop is in the direction of current always, because the resistor can only ever dissipate energy. The resistor cannot produce energy. So if there's power associated with a resistor, it's always positive, because the resistor just turns electricity into heat. So for that to be the case, the voltage drop has to be in the direction of the current. So that's just what I'm saying here. So then if we have a 2.4 volt drop from here to here, that means we have the same 2.4 volt drop from here to here. And now we basically end up with the same thing that we've done for all these questions. So if I zoom in on that 2 amp source, we have current going this way, and we have voltage here. So here we have voltage, I guess I should have phrased it this way earlier. Here we have voltage rising in the direction of current. When we have voltage rising in the direction of current, it's negative. When voltage is dropping in the direction of current, it's positive. So here, this will then be, the power is 0.2 amps times negative 2.4 volts, which is 0.48, negative 0.48 watts. Let me add that as a line here. Should have added this earlier. Okay, and with that, I'm like kind of out of time. There's one more question I'll get to here. But so you said, how did you get the first equation? Isn't it in equals out for V1? This is in equals out. It's just I wrote it, so you can either think of it as in equals out, or you can think of it as out minus in equals 0. And here I wrote it as out minus in equals 0. Yeah. Okay. So are there any final questions? I'll post this on like Google Drive and post it. Sorry if this first review session was a bit rambly. This first one's kind of hard because I don't know exactly what you've learned yet, so I don't know how from basics I have to talk stuff. Do I think there will be a transformation problem comparable to the last question of the homework? The homeworks in this class are generally much harder than the exams because, or not, they're not harder, but the homeworks in this class have more steps and are more convoluted than the questions you'll get on quizzes because you have much more time to do the homework than you have time to do the quizzes. So yes, the questions I did today were taken almost directly from previous quizzes. So yeah. Okay, no problem. Why did we add voltage sources in the second problem when they had opposite signs? Which, that was this one. Here, they do not have opposite signs. Here, this one is minus positive and this one is minus positive. So it's like going up in that direction and going up in that direction. So this 8 volt will add with that 8 volt to make a 16 volt. Do I recommend doing the practice problems in the textbook? If you want to, sure, it probably couldn't hurt. I generally like the homeworks are pretty good practice. He posts the answer keys for the homework after they're due. So look at those if you want. Yeah, do the practice problems in the textbook if you want. Uh, I don't really remember if those are I don't know what's on the quiz. They don't tell me what's on the quiz, so I can't exactly tell you which way or not. What did I write down for the negative voltage drop? Uh, Here you go. So it's if the voltage is dropping in the direction of the current, then we have positive. If the voltage is rising in the direction of current, then it's negative, which sounds counterintuitive, but that's the convention. It ends up it's nice because you generally have more resistors than you'll have like voltage sources. So you'll end up with more positive signs than negative signs. Yeah. Yeah, these notes will be posted too. And there's a lot of quizzes, so and you get like 2 quizzes dropped. So don't like throw on any quizzes, but you have some margin for error. Generally the first couple there's a couple quizzes that are harder than the others. I think you will all be fine, hopefully. And again, if you have more questions, I have office hours on Mondays, and Zorman has office hours, and I think Samantha has, or Dr. Johnson has office hours, and I think Melissa also has office hours. She's another TA. So if you want more like individual help, I would recommend going to those. Okay. With that, I will end the recording.